The quiet voyage of a lone photon. Let us begin our journey with a single photon. Just one particle of light. Imagine it now, floating in the darkness, waiting to tell its story. A photon is the quantum particle of light. It carries within itself a discrete packet of electromagnetic energy, so small, so simple, yet so essential to everything we see. This tiny messenger travels through space, bringing light, bringing warmth, bringing information across the cosmos. Breathe slowly now, and consider this remarkable thing. A photon has no rest mass, none at all. It is pure energy, pure motion, forever in flight. And yet, despite having no mass, it carries both energy and momentum. It can push against things. It can transfer its force. Without weight, it still has presence. Without substance, it still has power. In the vacuum of space, in the perfect emptiness between worlds, all photons travel at the same speed. The speed of light, approximately 300,000 kilometers per second. So fast that it could circle the Earth more than 7 times in a single second. And yet, on the cosmic scale we will explore tonight, even this incredible speed seems almost slow, almost patient, almost peaceful. The energy of a photon is proportional to its frequency. Higher frequency photons, those that oscillate more rapidly, carry more energy. They are more powerful, more intense. Blue light carries more energy than red light. Ultraviolet more than blue. X-rays more than ultraviolet. And at the highest frequencies, gamma rays. Pure concentrated energy in its most compact form. But do not concern yourself with these details now. Let them wash over you like a gentle wave. Here is something wonderful to contemplate as you relax. Photons exhibit both wave-like and particle-like behavior. This is called wave-particle duality. Sometimes, a photon acts like a particle, a tiny bullet of light traveling through space. Other times, it acts like a wave, spreading out, interfering with itself, creating patterns of light and shadow. Both descriptions are true. Both descriptions are incomplete. The photon simply is, beyond our everyday categories, beyond our need to classify. In the famous double-slit experiment, individual photons can interfere with themselves. One photon, traveling alone, somehow passes through 2 slits at once, creating an interference pattern as if it were a wave interacting with itself. This mystery has puzzled physicists for generations. But tonight, we need not solve it. We need only marvel at it. Let it fill us with wonder, and allow that wonder to carry us gently towards sleep. For visible light, a photon's wavelength determines its color. Short wavelengths appear violet to our eyes. Longer wavelengths appear blue, then green, then yellow, orange, and finally red. The longest wavelengths we can see. Each color is simply a photon vibrating at a different frequency, dancing to a different rhythm, singing a different note in the symphony of light. Photons can be absorbed, emitted, or scattered by matter. When a photon encounters an atom, it might be absorbed, transferring its energy to an electron, or it might be scattered, bouncing off in a new direction with a slightly different energy, or it might pass through completely undisturbed. Each interaction changes the photon's path, changes its energy, changes its story. And here is something absolute, something unchanging, A photon cannot slow down in vacuum. It either moves at the speed of light or it ceases to exist. There is no in-between, no gradual acceleration or deceleration. A photon is born traveling at light speed, lives its entire existence at light speed, and if it is absorbed, it simply ends. No slowing, no stopping, just existence, then non-existence. Finally, for this first part of our journey, consider polarization. This describes the orientation of a photon's electric field oscillation, the direction in which its electromagnetic wave vibrates. Vertical, horizontal, circular, diagonal. Each photon carries this property within itself, a hidden geometry, a secret orientation. And with this thought, let us move deeper into our story and deeper into rest. Now we trace the photon's origin, back to the beginning, back to the center of our sun, where all light is born in fire and fury, only to begin an impossibly long journey toward freedom. Most photons born in the sun originate in the core, the very center, the deepest place. Here, nuclear fusion converts hydrogen into helium. 4 hydrogen nuclei, 4 protons, collide and combine under extreme pressure and temperature, transforming into helium and releasing energy. Enormous quantities of energy. This is the fire that powers our star. This is the furnace where our photon begins its story. Fusion in the solar core reaches temperatures of about 15 million degrees Celsius. 15 million, a number so large it loses meaning. But imagine, if you can, a place so hot that atoms cannot hold together. A place where matter exists only as plasma. A soup of nuclei and electrons, stripped bare by the violence of heat. This is where our photon is born. In the proton-proton chain, the dominant fusion process in our sun, collisions between protons eventually produce helium nuclei and gamma-ray photons. These are the first photons, the original light. Born as gamma rays, the highest energy form of light. So energetic they could pass through meters of lead. So powerful they are dangerous to all life. But do not fear. This deadly radiation will transform, will soften, will become gentle before it reaches us. Just as the night transforms day into peaceful darkness. The initial photons created in the core are extremely energetic gamma rays, pure concentrated power. But the solar core is not empty space. It is not a clear path. It is dense, incredibly dense. The core is a dense plasma of protons and electrons, not neutral atoms. Matter compressed to over 150 times the density of water. In this crushing environment, our photon cannot simply escape. It cannot fly free. It must begin a very different kind of journey. The density and opacity of the core force photons into a random walk instead of a straight escape. Imagine a crowded room, so crowded you cannot walk in a straight line. You take one step forward and bump into someone. You turn. Take another step. Bump into someone else. Turn again. Step, bump, turn, step, bump. This is the photon's journey through the core. Not a path, but a wandering. Not a flight, but a stumble through an endless maze. Each absorption and re-emission event typically sends the photon off in a new random direction. The photon is absorbed by a particle, held for a moment, a brief moment, then re-emitted, but in a random direction. No memory of where it came from, no sense of where it needs to go. Just another step in the random walk, another turn in the maze. And this happens again, and again, and again, countless times, perhaps trillions of times. The photon's energy gradually degrades from gamma rays toward lower energy light during this random walk. Each time it is absorbed and re-emitted, each time it interacts with matter, it loses a little energy. The gamma ray becomes an X-ray. The X-ray becomes ultraviolet. The ultraviolet becomes visible light, like a river flowing downhill. The photon's energy flows down the spectrum, becoming gentler, becoming softer, becoming the light we know and need. The time to diffuse from core to surface is often estimated at hundreds of thousands of years. Some calculations suggest 100,000 years. Others suggest 1 million. The exact number depends on the model, depends on assumptions, but the scale is clear. Our photon, born in an instant, must spend an age just reaching the surface. Hundreds of thousands of years of random wandering. Hundreds of thousands of years of patient waiting. Time beyond human comprehension. Time that teaches us patience. Time that shows us that even light must wait. And here is something remarkable to contemplate as you drift. Neutrinos produced in the same fusion reactions escape the sun almost instantly compared with photons. Neutrinos barely interact with matter. They pass through the sun as if it were not there. In mere seconds, a neutrino born in the core emerges into space. But our photon, our patient photon, must take the long way, must pay the price of interaction, must learn every layer of the sun before it can leave. Let this thought settle over you like a blanket. Even light must be patient. Even light must wait its turn. Our photon continues its slow diffusion outward, through layers of the sun, each region different, each presenting new challenges, but always, always, moving gradually toward the surface, toward freedom, towards space. The sun's interior is divided into 3 main regions: the core, where we began, the radiative zone, which we now enter, and the convective zone, which awaits beyond. Each layer has its own character, its own physics, its own timescale. In the radiative zone, energy transport is dominated by radiation as photons scatter through plasma. This is still our photon's realm, still a place of absorption and re-emission, still a random walk, but through slightly less dense material. The journey continues. Above the radiative zone lies the convective zone. Here the physics changes. Hot plasma rises and cooler plasma sinks, moving energy primarily by bulk motion. Like water boiling in a pot, great columns of hot gas rise toward the surface, cool at the top, sink back down, rise again. A churning motion, a roiling. Our photon now rides these currents, still bouncing, still being absorbed and re-emitted, but now also carried by the motion of plasma itself, swept along in the great circulation of solar matter. As the photon undergoes an enormous number of scatterings, it effectively changes identity many times. The gamma ray that was born in the core no longer exists. It has been absorbed and re-emitted so many times, transformed so many times, that the current photon carries almost no connection to the original. It is like a story passed from person to person. Each telling changes it slightly. After thousands of tellings, millions of tellings, the story has transformed completely. Yet it carries forward some essence, some energy, some memory of its origin. The typical step between interactions in the dense interior is far smaller than a centimeter. Imagine. The photon travels less than the width of your finger before it encounters another particle, less than the distance from your thumb to your fingertip. At the speed of light, this takes an incomprehensibly short time, but multiply it by trillions of interactions, and suddenly, hundreds of thousands of years pass. This is the paradox of the photon's journey, moving at ultimate speed, yet taking eons to travel from center to surface, moving faster than anything, yet going nowhere quickly. By the time light nears the surface, its spectrum has shifted mostly into visible and infrared. The violent gamma rays of birth have been tamed. The dangerous X-rays have been softened. Now, the photon carries energies we recognize, energies that warm rather than destroy, energies that illuminate rather than ionize. The light has become gentle. The light has become life-giving. Let this transformation wash over you. Even the most violent beginnings can lead to peace. The photosphere, where most visible light escapes, has a temperature of roughly 5,500 degrees Celsius. This is the layer we see when we look at the sun, the surface, though there is no true solid surface, just the layer where plasma becomes thin enough, transparent enough, that photons can finally escape. After hundreds of thousands of years of captivity, after countless interactions, after a journey beyond imagination, the photon reaches the threshold of freedom. The visible surface of the sun is only a thin layer, a few hundred kilometers thick compared with the whole star. The sun's radius is nearly 700,000 kilometers, and yet the photosphere, the part we see, is just a few hundred kilometers thick, less than 1% of the radius, a skin, a membrane, the thinnest veil between the interior and space. And our photon must pass through this final barrier. Granulation patterns on the photosphere trace the tops of convective cells, bringing energy upward. If we could watch the sun's surface in detail, we would see a constantly changing pattern, like bubbles on boiling water. Each granule is the top of a convection cell. Hot plasma rising, spreading out, cooling, sinking back down. Our photon may ride one of these columns, carried upward by the churning plasma, brought to the surface by the sun's own restlessness. Magnetic activity in the solar atmosphere can further scatter or redirect some emerging photons. The sun has a magnetic field, complex, changing, creating sunspots where the field is strongest, creating loops and arches of magnetized plasma. Our photon might encounter these structures, might be scattered one more time, delayed slightly, redirected. But the end is near now. Freedom is close. Let yourself relax completely. Our photon has spent an age inside the sun, has been transformed beyond recognition, has traveled trillions of kilometers while moving only a fraction of the sun's radius. But now, finally, it approaches the moment of escape, the moment when its true journey begins. At last, after hundreds of thousands of years, after transformations beyond counting, after patience that transcends understanding, our photon emerges from the sun, breaks free, enters space, and discovers for the first time what it means to truly fly. Above the photosphere lie the chromosphere and the tenuous hot corona. These are the sun's atmosphere, layers of thin gas extending into space. The chromosphere is a reddish layer, visible during solar eclipses. Above it, the corona, vast, mysterious, beautiful. the corona reaches temperatures of millions of degrees Celsius, much hotter than the surface. This seems impossible. How can the atmosphere be hotter than the surface? Scientists still debate the details. Perhaps magnetic energy, perhaps wave heating. But the fact remains, the corona is millions of degrees. And yet, paradoxically, it poses little threat to our photon now. The density in the corona is so low that a photon can travel far before interacting. Unlike the dense interior, where every step brought a collision, here in the corona, the photon can travel for meters, for kilometers, for thousands of kilometers, without hitting anything. The path is nearly clear, nearly empty. The photon accelerates away from the sun, though of course it was always traveling at light speed. Rather, it now travels in a straight line. For the first time since its birth. A straight line. No more random walk, no more scattering. Just pure flight, pure freedom. Outward streaming photons exert radiation pressure. This is a force that can push on dust or solar sails. Light has no mass, but it carries momentum. When a photon hits something and is absorbed or reflected, it transfers that momentum, pushes. This is radiation pressure. Gentle, but real. The light leaving the sun pushes outward on everything around it. Dust grains, molecules, hypothetical solar sails that might one day carry spacecraft on beams of light. Even you, standing in sunlight, feel a tiny push from photon momentum. Too small to notice, but real. Let this thought comfort you. The light touches everything, gently, persistently, lovingly. Once beyond the corona, a photon effectively travels through interplanetary space with few encounters. Now the journey becomes simple. Now the photon flies true, through the vacuum of space, past Mercury, past Venus, toward Earth, perhaps, or perhaps in another direction entirely. Past Mars, past the asteroid belt, past Jupiter, outward, always outward, at 300,000 kilometers per second. Fast beyond imagination. And yet, even at this speed, space is so vast that the journey takes time. A photon crossing the average Sun-Earth distance takes about 8 minutes. This is our next milestone. 8 minutes. The Sun is about 150 million kilometers from Earth. 1 astronomical unit. A distance so vast that even light, traveling at its cosmic speed limit, needs 8 minutes to bridge it. When you look at the Sun, you see it not as it is now, but as it was 8 minutes ago. You see into the past. 8 minutes into the past. The light that reaches your eye began its final journey through space before you finished your last thought, before you drew your last few breaths. Time and space interweave in strange ways at these scales. The Sun-Earth distance is about 150 million kilometers, 1 astronomical unit. We use this distance as a ruler for the solar system. Mercury orbits at about 0.4 astronomical units, Mars at about 1.5, Jupiter at 5.2, Saturn at 9.5. We measure the solar system in units of light minutes and light hours, the natural measure of distance when you travel at the speed of light. Photons headed inward toward planets can be scattered by planetary atmospheres or surfaces. Our photon might encounter Earth, might pass through the atmosphere, scattering off air molecules, turning the sky blue, might strike the ground, warming the soil, might be absorbed by a leaf, driving photosynthesis, becoming life. might enter an eye, animal or human, triggering a visual signal, becoming sight. Or it might miss Earth entirely, might pass through the thin shell of orbit, continuing outward, untouched, unnoticed, heading deeper into space. A photon that misses all planets and small bodies will continue outward into interstellar space. Most photons do miss. Space is mostly empty. Even in our solar system, crowded by cosmic standards, the planets are tiny targets in a vast shooting gallery. Our Sun emits about 3.8 times 10 to the 26th watts of power. Incomprehensibly many photons every second. Most fly outward, most encounter nothing. Most begin the long journey to the stars. After just a few hours, a photon can be well beyond Pluto's orbit if emitted radially outward. Pluto orbits at about 40 astronomical units. At light speed, this is about 40 times 8 minutes, about 5.5 hours. By the time you wake from a good night's sleep, our photon could be beyond the orbit of the farthest recognized planet, beyond the realm of the major worlds, entering the outer solar system, the realm of comets and dwarf planets, the realm of frozen darkness, the edge of the sun's domain. Let your breathing slow even further now. Our photon has escaped the sun, has crossed the inner solar system, has reached the outer darkness, but the journey has barely begun. Space stretches on, empty, patient, eternal, and our photon flies forever onward. We drift now into the outer reaches of the solar system, a realm of cold and darkness, where the sun appears only as a bright star, where our photon continues its steady flight outward, undeterred by the emptiness, undimmed by the distance. The solar system is filled with the solar wind, a stream of charged particles from the sun, mostly protons and electrons, flowing outward at hundreds of kilometers per second, slower than light, but still fast by human standards. This solar wind creates a bubble around the sun, a magnetic bubble. Our photon passes through this wind without interaction. Light does not couple to the solar wind, but the wind defines the boundary of the sun's influence, and that boundary lies ahead. Interplanetary dust can scatter and absorb some photons, creating phenomena like zodiacal light. If you stand in a truly dark place, away from city lights, and look west after sunset or east before sunrise, you might see a faint glow along the ecliptic, the plane of the solar system. This is zodiacal light, sunlight scattered by countless tiny dust particles, debris from comets, debris from asteroids. Each grain catches photons, scatters them, creates a gentle glow. Most photons pass through undisturbed, but some, a few, paint the sky with their scattering. Reflected sunlight from dust and planets dominates the visible brightness of the inner solar system. When we see Venus, when we see Mars, when we see Jupiter, we are not seeing light from these worlds themselves. We are seeing reflected sunlight, photons that left the sun, struck a planet, bounced off, and entered our eyes. The planets shine with borrowed light, as does the moon, as does everything that does not generate its own light. We live in reflected glory. We see by borrowed photons. Some photons are absorbed by dust grains and re-emitted at longer infrared wavelengths. This is thermal re-emission. A dust grain in space absorbs visible light, heats up, glows in the infrared. The photon's energy is not lost, but transformed again, changed from visible to infrared, from what we can see to what we can only feel as heat. The photon's identity shifts once more, but its energy continues forward, continues the journey in a new form. Gravitational fields of planets bend photon paths slightly. This is gravitational lensing, though usually very weak here in the solar system. Einstein taught us that mass curves space-time, and light follows the curves of space-time. So a photon passing near a planet, near the Sun, near any mass, has its path bent slightly. Usually this effect is tiny, negligible, but it is real. Space itself curves, and light follows faithfully along those curves, like a marble rolling on a stretched rubber sheet. Let this image comfort you. The universe has geometry, structure, order beneath the apparent chaos. A photon can pass near giant planets like Jupiter with effectively no interaction, if it does not hit an atmosphere or ring particle. Jupiter is huge, vastly larger than Earth. And yet, even Jupiter is a tiny target against the backdrop of space. Our photon likely passes by all the giants. Jupiter, Saturn, Uranus, Neptune, sees them from a distance perhaps, if photons could see, flies past their orbits, continues outward, into the realm beyond planets, into true deep space. The heliosphere marks the region where the solar wind dominates over the interstellar medium. This is the Sun's sphere of influence, the magnetic bubble it carves out of the galaxy. Inside the heliosphere, we are in the Sun's domain. Outside, we enter interstellar space, the realm between stars. The heliopause is the boundary where the solar wind's pressure balances that of interstellar gas. Not a sharp wall, but a gradual transition. A zone where the Sun's influence fades, where the galaxy's influence grows, where one realm gives way to another. Light crosses the size of the heliosphere in less than a day. The heliosphere extends to perhaps 100 to 120 astronomical units, perhaps more in some directions, less in others. The boundary shifts, flexes, breathes with the solar cycle. But roughly, we can say 100 astronomical units. At 8 minutes per astronomical unit, this is about 800 minutes, about 13 hours, in half a day. Our photon crosses from the inner solar system to the edge of the heliosphere. Half a day. And yet, from humanity's perspective, this is already beyond our reach. The Voyage spacecraft, our fastest and most distant ambassadors, took decades to reach the heliopause. But light makes the journey while you sleep. Photons escaping beyond the heliopause continue their voyage through the interstellar medium of the Milky Way. This is the next great transition, from the solar system to the galaxy, from the realm of the Sun to the realm of stars. The heliosphere falls behind. The Sun diminishes to a point of light, one star among billions, and our photon flies on, enters the interstellar medium, the space between stars, the great ocean of the galaxy. And here, the journey becomes truly cosmic, truly vast, truly eternal. Rest now. Let these distances wash over you. Distances measured in light hours, soon to become light years, soon to become unimaginable. But for now, rest, breathe, float in the darkness between worlds. Our photon continues, patient, eternal, flying through the void. Now we enter the space between stars, the interstellar medium, a place that seems empty, yet is not. A place that seems dark, yet is filled with hidden light. Our photon flies through this realm, encountering new challenges, new interactions, but always continuing forward, always traveling toward the edge of the galaxy. The interstellar medium contains gas, mostly hydrogen and helium, and dust grains. This is the substance between stars. Not empty vacuum, but thin, unimaginably thin, wisps of matter. Hydrogen atoms, helium atoms, molecules. Grains of dust smaller than particles of smoke. This is the medium through which our photon must pass. This is the final gauntlet between the Sun and the galaxy's edge. Average interstellar densities are extremely low, often just a few atoms per cubic centimeter. Imagine a cube, 1 centimeter on each side, the size of a sugar cube. In the air you breathe, such a cube contains about 10 to the 19th molecules. 10 billion molecules. In the interstellar medium, the same cube might contain 10 atoms, perhaps 100, perhaps just 1. Emptier than the best vacuum we can create on Earth. Emptier than anything in human experience. And yet, over vast distances, even this tenuous matter adds up. Even at these low densities, cumulative absorption and scattering shape the light from distant stars. 1 atom per cubic centimeter seems like nothing, but multiply by thousands of light years, by trillions of kilometers, and suddenly, that thin gas becomes an obstacle, not a wall, but a filter, a gradual dimming, a selective absorption. The interstellar medium shapes the light that crosses it, changes it, marks it with its presence. Dust preferentially blocks blue light, making distant stars appear redder. This is interstellar reddening. Blue light has shorter wavelengths. It scatters more easily off small particles. Red light has longer wavelengths. It passes through more easily. So as light travels through dust, the blue is scattered away and the red remains. Distant stars appear redder than they truly are. Not because they are cooler, not because they are moving away, but because the dust between us and them has filtered out the blue, has changed the color of their light. This teaches us caution. What we see is not always what is. The medium shapes the message. Some photons are absorbed by atoms or molecules, exciting them to higher energy levels. An atom in its ground state, peaceful, low energy. A photon arrives, the atom absorbs it. An electron jumps to a higher orbital. The atom is now excited, agitated. It holds this energy for a moment, perhaps a microsecond, perhaps a millisecond, then it relaxes, releases the energy, but perhaps not in the same direction, perhaps not at the same wavelength. The photon's journey has been interrupted, redirected, changed. After absorption, re-emission can send a new photon off in a random direction, effectively removing the original from the beam. If you are looking at a distant star, waiting for a particular photon, and that photon is absorbed and re-emitted by an atom between you and the star, it might be re-emitted toward you, but probably not. Probably it is scattered in some other direction, lost to you, lost to any observer looking along that line of sight. The beam of light is weakened, diluted, spread across a wider angle. This is how the interstellar medium dims starlight. Certain wavelengths form characteristic absorption lines in stellar spectra. due to specific elements in the interstellar medium. Hydrogen absorbs specific wavelengths. Calcium absorbs others. Sodium, carbon, oxygen. Each element has its signature, its fingerprint in the spectrum. When we examine light from distant stars through a spectrograph, we see dark lines. Gaps in the rainbow. These are absorption lines. Some come from the star's own atmosphere, but some come from the interstellar medium. The gas between us and the star has removed specific colors, left its mark, told us what lies in the space between. In dense molecular clouds, dust can become nearly opaque to visible photons. There are regions in the galaxy, dark nebulae, where dust is so thick that visible light cannot penetrate. These appear as dark patches against the background stars, not because nothing is there, but because dust is there. So much dust that light cannot pass. The photons are absorbed, scattered, blocked. The cloud is dark to our eyes, but not truly dark, not truly empty, just opaque. Infrared photons penetrate dust clouds more easily than visible photons. This is a key tool for astronomers. If a region is dark in visible light, look in infrared. The longer wavelengths pass through the dust, reveal what is hidden, show the stars forming inside, show the structure within. Our photon, if it were infrared, would face less obstacle, would penetrate deeper, would travel farther before being stopped. But visible light, the light our eyes evolved to see, is more easily blocked, more easily scattered, more vulnerable to the dust. Over tens of thousands of light years, interstellar extinction can dim starlight by many magnitudes. Magnitude is the astronomer's measure of brightness. Each magnitude is a factor of about 2.5 times in brightness. Extinction of several magnitudes means the star appears several times, even 10 times, 100 times, dimmer than it would in empty space. The galaxy is not transparent. The medium is not invisible. Distance comes with a cost, a gradual fading, a slow dimming, until eventually, the light is lost entirely, absorbed, scattered, transformed, gone. Breathe deeply, rest in this knowledge. Even light must struggle. Even photons face obstacles. But some persist, some continue, some reach the edge. And our photon, our single photon, flies on. Diminished perhaps, reddened perhaps, but still traveling. Still carrying its message, still heading for the galactic frontier. Our photon now travels through the great spiral of the Milky Way, our galaxy, our island in space, a gathering of hundreds of billions of stars, bound together by gravity, rotating slowly, evolving over eons. And through this vast structure, our single photon makes its way, a messenger from one star, heading toward the edge, heading toward the darkness beyond. The Sun orbits the center of the Milky Way at roughly 8 kiloparsecs from the galactic center, about 26,000 light-years. A kiloparsec is 1,000 parsecs. A parsec is about 3.3 light-years. These are the natural units of galactic astronomy. The Sun is not at the center of the galaxy, not at the edge, but in between, in a spiral arm, in the galactic suburbs, orbiting slowly, taking about 230 million years to complete one orbit. The Sun has orbited the galaxy perhaps 20 times since it formed, perhaps more. It is on a long journey of its own, a journey measured in eons. A photon emitted from the Sun in the galactic plane can, in principle, traverse tens of thousands of light-years within the galaxy. This is our photon's potential. If it travels outward, away from the galactic center, and if it is lucky, if it avoids absorption, if it avoids scattering, it might travel 10,000 light years, 20,000, 30,000, perhaps even farther. Each light year is about 9.5 trillion kilometers, vast beyond human conception. And our photon might cross tens of thousands of them, but only if it is lucky, only if its path is clear. The Milky Way's disk contains spiral arms, rich in gas, dust, and young stars that a photon may pass through. These are the bright lanes of the galaxy, where stars are being born, where gas is dense, where dust is thick. The spiral arms are beautiful in photographs, glowing regions of pink hydrogen, dark lanes of dust, clusters of bright blue stars. But for our photon, the spiral arms are obstacles, regions of high extinction, regions where absorption is more likely. If our photon passes through a spiral arm, its journey becomes more perilous. Its chances of absorption increase. Star-forming regions within spiral arms are particularly dusty and opaque at visible wavelengths. The Orion Nebula, the Eagle Nebula, the Carina Nebula. These are stellar nurseries, places where clouds of gas collapse under their own gravity, fragment, form stars, beautiful to see, but dark in their hearts. The densest regions are so thick with dust that no visible light escapes, only infrared, only radio waves. Our photon, if it encounters such a region, will likely be absorbed, transformed. Its journey as visible light ended, perhaps re-emitted as infrared, perhaps locked in a grain of dust, perhaps incorporated into a new star system. The journey continues, but not as the same photon. The galactic halo is a more diffuse region of hot gas, old stars, and dark matter, extending beyond the disk, above and below the plane of the galaxy. The halo is quieter, older, less dense. If our photon's trajectory takes it out of the galactic plane, up into the halo or down below, it enters a clearer region. Fewer obstacles, less dust, lower density. The halo offers an easier path, a longer potential journey, a better chance of reaching the edge. Photons exiting the disk into the halo encounter lower densities of gas and dust overall. The halo is not empty, but it is emptier than the disk. An atom per cubic centimeter in the disk becomes an atom per 100 cubic centimeters in the halo. Perhaps less. The extinction rate drops. The probability of absorption decreases. Distance that would be opaque in the disk becomes transparent in the halo. Our photon breathes easier here, flies freer, faces fewer challenges. The galactic magnetic field affects charged particles but does not directly deflect photons. The galaxy has a magnetic field, weak but present, threading through the disk, channeling the motion of electrons, guiding cosmic rays. But photons, neutral, uncharged, pass through magnetic fields without deflection. The field is invisible to light. The field does not interfere with our photon's path. Only gravity and matter can change a photon's trajectory. Only absorption and scattering. Massive objects like star clusters and dark matter concentrations can slightly bend photon paths via gravity. This is gravitational lensing again, but now on galactic scales. A cluster of stars, a concentration of dark matter. These create gravitational wells, curves in space-time, and our photon, following the geometry of space-time, curves slightly as it passes. The deflection is tiny, a fraction of an arc-second, but over thousands of light-years. Even tiny deflections add up. The photon's path is not perfectly straight. It curves, bends, follows the invisible architecture of mass and space-time. The sun's own motion around the galaxy does not change the photon's speed, only the frame from which it is measured. The sun moves at over 200 kilometers per second in its orbit. The photon moves at 300,000 kilometers per second. But these motions do not add in the simple way we might expect. Special relativity teaches us that light speed is constant in all reference frames. To us, riding with the sun, the photon moves at light speed. To an observer at the galactic center, the photon still moves at light speed. The speed of light is absolute, universal, unchanging. Let this absolute constancy soothe you. Some things do not change. Some things remain forever constant. Over millions of years, the photon's path effectively traces a nearly straight geodesic through curved space-time. A geodesic is the straightest possible path through curved space, like a great circle on Earth's surface. The photon follows the geometry, curves where space-time curves, travels straight where space-time is flat, over human timescales, over thousands of years, even over millions of years. The path appears almost perfectly straight. Only the most careful measurement would reveal the gentle curves, the subtle bends. The photon flies true, flies straight, flies eternally toward its destination, whatever that may be. Now we approach the frontier, the edge of the Milky Way, the boundary between our galaxy and the void beyond. This is not a wall, not a barrier, but a gradual fading, a thinning, a transition from one realm to another. Our photon draws near to this threshold, having traveled so far, having endured so much, now approaching the moment when it might leave the galaxy entirely. The edge of the Milky Way is not a sharp boundary, but a gradual thinning of stars and gas. There is no sign that says, "You are now leaving the Milky Way." No clear demarcation. Instead, star density decreases, gas density decreases, dust density decreases, gradually, smoothly, like walking from a forest into a meadow. The trees thin out, become scattered, finally disappear. But there was no fence, no line, just a transition, just a change. The stellar disk likely extends to roughly 50 to 60,000 light-years in radius. This is the main body of the galaxy, where most stars live, where the spiral arms reside. The Sun is about 26,000 light-years from the center, so the edge of the disk is about 24 to 34,000 light-years beyond us. Our photon, if it travels radially outward from the Sun, might reach this boundary, might leave the main disk, might enter the sparse outer regions where few stars remain. The dark matter halo extends far beyond the visible disk, possibly hundreds of thousands of light-years. Dark matter does not emit light, does not absorb light, interacts only through gravity. We know it exists because of its gravitational effects on visible matter, on the rotation of the galaxy, on the motion of stars. The dark matter halo is vast, invisible, mysterious. It extends far beyond the stars we can see, creates a deep gravitational well, binds the galaxy together. Our photon passes through this halo without noticing, without interaction. The dark matter is invisible not just to our eyes, but to the photon itself. A photon passing through the outer disk sees far fewer stars per unit volume than in the inner regions. Imagine standing in a crowded city, then walking to the suburbs, then to the countryside, then to the wilderness. The number of people per square kilometer drops dramatically. Similarly, in the outer galaxy, star density drops. In the inner galaxy near the center, stars are packed tightly, close enough that their light overlaps, their gravity interacts. But out here, at the edge, stars are lonely, scattered, separated by vast gulfs of space. In the outskirts, interstellar dust density is lower, so extinction effects weaken. This is good news for our photon. Less dust means less absorption, less scattering. A clearer path. Light travels farther before being blocked. The outer galaxy is clearer, more transparent. Our photon has a better chance here. A better chance of continuing, of escaping, of reaching truly intergalactic space. Beyond the main stellar disk, most potential interactions are with sparse gas in the halo, or high-velocity clouds. These are clouds of gas moving at unusual velocities, perhaps falling into the galaxy from outside, perhaps ejected by ancient supernovae. They drift through the halo. Occasionally our photon might encounter one, might be absorbed or scattered, but these clouds are rare, small targets in a vast volume, most likely. Our photon passes through empty space, through the tenuous halo, through the outer reaches, undisturbed. A photon that escapes the galactic disk can still be gravitationally bound to the galaxy. Light itself, however, always moves at c. There is an interesting question here. Can light escape the galaxy's gravity? The answer is subtle. Photons always travel at light speed. They cannot be slowed, cannot be captured, but their paths can be curved, bent back toward the galaxy. In principle, a photon traveling outward could have its path bent so much that it curves back, falls back into the galaxy. But the galaxy's gravity is not strong enough for this, not for photons traveling outward from the outer disk. Our photon will escape, will leave the galaxy, will enter intergalactic space. To an outside observer, the Milky Way's integrated starlight is built from enormous numbers of such photons escaping the disk. Every galaxy we see in the night sky, every distant spiral, every elliptical, every irregular dwarf, we see them because photons escape. Billions of trillions of photons, each carrying a tiny bit of information, a tiny bit of energy. Together they paint the image of the galaxy. Our photon is one of these. One ambassador from the Milky Way to the wider universe. One tiny messenger in an endless stream. Some sun-emitted photons today are already tens of thousands of light years away and leaving the galaxy's visible disk. Think of this. Right now, at this very moment, photons that left the sun tens of thousands of years ago are crossing the galactic frontier. When those photons left, humans were still in the Stone Age. Agriculture had not been invented. Writing did not exist. Cities had not been built. And those photons have been traveling all this time, crossing the galaxy, approaching the edge, about to leave, about to become intergalactic travelers. Time and space interweave in ways that humble us, that remind us of our smallness, that invite us to rest in the vastness. Let us pause now in our journey. Take a moment to reflect on the deeper physics, the stranger aspects of light, the quantum nature of our photon, the relativistic effects, the ways in which light transcends our everyday experience. These thoughts can carry us deeper into rest, deeper into wonder, deeper into the peaceful contemplation of the cosmos. In its own reference frame, if such could be meaningfully defined, a photon experiences no passage of proper time. This is one of the strangest consequences of relativity. Time dilation. As you approach the speed of light, time slows down relative to the outside world. At the speed of light, time stops completely. From the photon's perspective, if it had a perspective, the journey from the Sun to the edge of the galaxy takes zero time. Emission and absorption are simultaneous. Birth and death are the same moment. The entire journey, hundreds of thousands of years from our perspective, is instantaneous from the photon's perspective. Let this impossible idea wash over you. Do not try to understand it fully. Just marvel at it. Just rest in its strangeness. From an external frame, the photon can take millions or billions of years to cross galactic distances. This is our perspective. The perspective of matter, of observers at rest or moving at ordinary speeds. We watch the photon fly, we measure its position, track its progress, and we find that it takes time, real time, measurable time. To cross the galaxy at the speed we have been discussing, tens of thousands of light years takes tens of thousands of years. Longer if the path is not straight. Longer if there are detours. Longer if the photon is scattered. But always, from our perspective, the journey takes time. We experience duration. We experience change. We experience the passage of years. Even if the photon does not. Gravitational redshift slightly changes photon energy when climbing out of gravitational wells. When a photon leaves the Sun, it must climb out of the Sun's gravitational well. This requires energy. The photon's energy decreases slightly. Its wavelength increases. It becomes redder. This is gravitational redshift. The effect is small for the Sun, larger for more massive objects. For a neutron star, for a black hole, near a black hole's event horizon, gravitational redshift becomes extreme, infinite at the horizon itself. But our photon, leaving the Sun, experiences only a tiny shift, a small change, barely measurable, but real. Another mark left by the journey. Passing near massive objects in the galaxy can cause tiny deflections known as weak gravitational lensing. We mentioned this before, but it bears repeating. As the photon travels across the galaxy, it passes near stars, near star clusters, near molecular clouds. Each one curves space-time slightly. Each one deflects the photon slightly. The deflections are tiny, but they accumulate. Over tens of thousands of light years, the path might deviate by an arc-second. By a degree, maybe more. The photon's trajectory is not perfectly straight. It wiggles, curves, follows the lumpy distribution of mass in the galaxy, reads the invisible map of gravity. Space-time expansion is negligible on galactic scales compared with gravitational binding. The universe is expanding. Distant galaxies are receding from us, but this expansion is only significant on the largest scales. Scales of hundreds of millions of light years, billions of light years. On galactic scales, gravity dominates. The Milky Way is gravitationally bound. It is not expanding. The Andromeda Galaxy is actually moving towards us, not away, because local gravity overcomes cosmic expansion. Our photon's journey across the galaxy is not affected by expansion. The galaxy is too small, too tightly bound. Expansion happens only in the voids between galaxy clusters. in the vast empty spaces of the cosmos. Over cosmological distances beyond the galaxy, universal expansion would stretch the photon's wavelength. This is cosmological redshift. If our photon continues beyond the galaxy, beyond the local group, beyond nearby galaxy clusters, into truly intergalactic space, then expansion becomes important. The wavelength stretches, the photon redshifts. Over billions of light years, a photon emitted in the ultraviolet might arrive in the infrared. A photon emitted in the visible might arrive in the microwave. The universe itself changes the light that crosses it. This is how we know the universe is expanding. This is how we measure cosmic distances. By the redshift of light, by the stretching of photons. Single photon experiments in laboratories demonstrate phenomena like interference, entanglement, and quantum teleportation, similar to what photons could in principle show in space. In the lab, we can control photons, send them through beam splitters, create entangled pairs, measure them in different bases, demonstrate the weirdness of quantum mechanics, interference, superposition, entanglement, non-locality. All these phenomena are real, all have been demonstrated, and in principle, they apply to our photon as well. Out in space, alone, traveling through the galaxy, it is still a quantum object, still described by a wave function, still subject to the strange rules of quantum mechanics. Quantum measurements, such as detecting a photon with a telescope, irreversibly collapse its quantum state. This is the measurement problem, the central mystery of quantum mechanics. Before measurement, the photon exists in a superposition, a probability cloud. It has no definite position, no definite momentum, both and neither at once. But when we detect it, when a telescope catches it, when it strikes a detector, the wave function collapses. The photon appears at a specific place, at a specific time. The superposition ends. The measurement creates reality, or reveals reality, depending on your interpretation. Let this mystery lull you. Some things have no answer. Some things remain mysterious. And that is okay. That is beautiful. Between emission and detection, a photon is best described by a quantum wave function spread over space. This is the modern picture. The photon is not a little ball traveling through space. Not really. It is a field, a probability amplitude, spread out, delocalized. The wave function tells us where we might find the photon if we look. But until we look, the photon is everywhere and nowhere, potential rather than actual. This picture is strange, counterintuitive, impossible to visualize properly, but it is the best description we have, the most accurate, the most complete. And somehow, this quantum picture gives rise to the classical world we experience, the world of definite positions, definite trajectories, definite outcomes. The quantum becomes classical through decoherence, through interaction with the environment, through the accumulation of countless measurements. But the quantum remains underneath, always, forever. The probability of detection at any point along its path is governed by that wave function and the presence of matter or detectors. This is the Born rule, the fundamental law connecting quantum mathematics to observable reality. The wave function is a complex number at each point in space. The probability of finding the photon at a point is the absolute square of the wave function there. Where the wave function is large, detection is likely. Where it is small, detection is unlikely. Where matter exists, Where detectors exist, the probability concentrates. The photon is pulled toward measurement, toward interaction, toward collapse. And finally, eventually, inevitably, the photon is detected, absorbed, measured, and its journey ends. Its wave function collapses. Its quantum existence becomes classical memory. Let yourself collapse now into rest, into sleep, into the peaceful end of consciousness. The photon's journey mirrors our own drift into unconsciousness. Quantum becoming classical, potential becoming actual, waking becoming sleep. And now we come to the end, the final segment of our journey. Where does our photon's voyage conclude? How does its story finish? There are many possible endings, many possible fates. Let us explore them together, gently, peacefully, as we ourselves approach the end of waking, the beginning of sleep, the transition from day to night, from consciousness to dreams. A sun-born photon can end its journey by being absorbed in an eye on Earth, generating a visual signal. This is perhaps the most poetic ending. The photon leaves the sun, crosses 8 light minutes of space, enters Earth's atmosphere, passes through air, through a lens, strikes a retina, is absorbed by a molecule called rhodopsin in a rod or cone cell. The rhodopsin changes shape, triggers a cascade of chemical reactions, generates an electrical signal. The signal travels along the optic nerve, reaches the brain, and becomes sight, consciousness, awareness. The photon's energy becomes an image, becomes perception, becomes experience. You have caught countless photons this way. Your eyes are photon catchers. Every color you see, every image, every face, built from photons, built from light. The universe sees itself through your eyes. Through the photons it sends you. It can be absorbed by a planetary surface, heating the ground or driving chemical reactions like photosynthesis. This is another common fate. The photon strikes soil, rock, water, is absorbed. Its energy becomes heat, warms the surface, warms the planet, or perhaps it strikes a leaf, is absorbed by chlorophyll. Its energy splits water molecules, drives the synthesis of sugars, powers photosynthesis, powers life. All plants are photon-powered. All food chains begin with photosynthesis, begin with captured sunlight, begin with photons like ours. The photon's journey ends, but its energy continues, flows into life, into growth, into the great cycle of energy on Earth. It may strike a solar panel, liberating electrons and contributing to electric power. This is the modern ending, the technological ending. The photon strikes a semiconductor, silicon perhaps. Its energy excites an electron, kicks it into the conduction band. The electron flows, becomes current, becomes electricity, powers a light, a computer, a city. The photon becomes useful, becomes harnessed, becomes part of human civilization. Its 8-minute journey from sun to Earth, its hundreds of thousands of years journey from core to surface, ends in a flash of electricity, a moment of power, a contribution to our modern world. Far from the sun, it might be absorbed by a dust grain in the interstellar medium and re-emitted in the infrared. If our photon never reaches a planet, never reaches a star, if it travels into the deep interstellar medium, eventually, probably, it will hit a dust grain, be absorbed. Heat the grain glows faintly in the infrared. Thermal emission, the photon has changed form, visible to infrared, light to heat, energy to energy. The journey continues in a new form, a longer wavelength, a lower energy, but still traveling, still carrying information. still part of the great flow of energy through the cosmos. A photon can be captured by gas in a distant star-forming region, adding to its emission spectrum. Perhaps our photon travels thousands of light years, encounters a nebula, a cloud of hydrogen and helium, is absorbed by a hydrogen atom. The electron jumps to a higher level, holds the energy briefly, then drops back down, re-emits the photon, but now the photon carries a specific wavelength. The wavelength of hydrogen alpha, or hydrogen beta, or some other spectral line. The photon has become part of the nebula's spectrum, part of its glow, part of its beauty. The nebula shines brighter by one photon, and our photon's journey becomes part of a new star's story. Some photons will escape the Milky Way entirely, contributing to the diffuse background light in intergalactic space. This is the grandest ending. The photon leaves the galaxy, enters the void. The space between galaxies is not completely empty. There is light there, faint, diffuse, but real. The extragalactic background light, built from photons that escape their home galaxies. Our photon might become part of this background, might travel through intergalactic space for billions of years, might be seen by an astronomer in a distant galaxy, part of the Milky Way's faint glow, part of our galaxy's light signature, a messenger we sent, knowingly or not, to the wider universe. If never absorbed, the photon would continue across the expanding universe indefinitely, gradually redshifting. This is the eternal journey. The photon that never ends. It leaves the galaxy, travels through intergalactic space. The universe expands around it. Its wavelength stretches. Visible becomes infrared. Infrared becomes microwave. Microwave becomes radio. The energy decreases. The wavelength grows. But the photon continues, forever, or until the heat death of the universe, whichever comes first, a particle of light, alone, in the expanding void, carrying its tiny bit of energy into the infinite future. This is not sad. This is peaceful. This is eternal. Like consciousness fading into sleep, like thought dissolving into dreams. The photon journeys on, forever, peacefully, into the endless night. Human instruments, such as telescopes and cameras, rely on detecting individual photons from distant sources. Every image from the Hubble Space Telescope, every photograph of a distant galaxy, every spectrum of a faraway quasar, built from individual photons, one at a time, accumulated over hours of exposure. Each photon traveled billions of light years, crossed most of the observable universe, to arrive at our telescope, to be detected, to be counted, to be transformed into knowledge. We see the universe one photon at a time, each one carrying information, each one a messenger, each one a gift from the distant cosmos. And we are grateful. We are awed. We are humbled by the journeys these photons have made to reach us. Detailed studies of photons from the Sun and beyond reveal the structure and history of the galaxy by analyzing light, by studying spectra, by measuring wavelengths and intensities and polarizations. We learn about the universe. We learn about the composition of stars, the temperature of nebulae, the distance to galaxies, the age of the universe, the expansion rate, the presence of dark matter, all from light, all from photons, carrying information across space and time. The universe speaks to us in photons, and we have learned to listen, have learned to decode the messages, have learned to read the cosmic story written in light. Artistic and educational projects often personify a single photon's voyage to help convey the scale and wonder of cosmic distances. This is what we have done tonight. We have followed one photon, from birth to potential death, from the sun's core to the galaxy's edge. We have used this single particle to understand the cosmos, to feel the distances, to grasp the timescales, to appreciate the journey. This is the power of story, the power of narrative, to make the abstract concrete, the vast comprehensible, the incomprehensible somehow felt. You have journeyed with this photon. You have crossed space and time. You have witnessed the universe, and now it is time to rest. Let us begin, in stillness, in wonder, by understanding what a photon truly is. Before we follow its journey, before we trace its path across the cosmos, we must first know the traveler itself. Breathe slowly now, and let these ideas wash over you like gentle waves. Photons are bosons with spin 1. This allows many photons to occupy the same quantum state. Think of this for a moment. Particles come in two types. Fermions, which are solitary, exclusive. No two can share the same state. And bosons, which are gregarious, collective. Infinitely many can pile into the same quantum state. Photons are bosons. This is why lasers work. This is why light can be so intense. Countless photons, all marching in perfect step, all sharing the same quantum state, all moving as one. A collective, a choir, a symphony of light singing the same note in perfect unison. Unlike massive particles, photons have no rest frame. The idea of a photon's clock is only metaphor. This is profound. Every particle you know, every atom, every electron, every proton can be brought to rest, can sit still in some reference frame, has a rest frame where time passes normally, but not the photon. The photon is always moving, always at light speed. There is no reference frame where a photon sits still. There is no photon's perspective, no photon's clock ticking away the seconds. When we speak of the photon's journey, when we personify its voyage, we speak in metaphor, in poetry, not in physics. The photon experiences nothing, knows nothing, simply is, simply moves, simply exists as pure energy in eternal motion. A photon's momentum equals its energy divided by the speed of light. This enables tiny radiation pressure. Even without mass, photons push, they carry momentum. When a photon strikes a surface and is absorbed, it transfers this momentum. The surface feels a push, tiny, gentle, but real. This is radiation pressure, the pressure of light itself. Solar sails could one day ride this pressure, pushed by photons, sailing through space on beams of sunlight. Every time light touches your skin, you feel a tiny push, too small to notice, but there, always there. The light touches everything, pushes everything, moves everything, gently, persistently, lovingly. Photons can be entangled in polarization or frequency, even across large separations. This is one of the deepest mysteries of quantum mechanics. Two photons can be created together, connected, entangled. They fly apart, perhaps light years apart, yet they remain connected. Measure the polarization of one, and instantly, somehow, the other's polarization becomes determined. Not because of any signal passing between them, not because of any hidden instruction they carry, but because they are entangled. Because at the quantum level, they remain one system, two particles acting as one. Distance means nothing to entanglement. Separation is an illusion. At the quantum level, Everything that has ever interacted remains connected. Forever. Infinitely. Mysteriously. The coherence length of sunlight photons is relatively short due to the sun's broad spectrum. Coherence is the distance over which light maintains a definite phase relationship. Laser light is highly coherent. The waves march in step for meters, for kilometers. But sunlight, created by countless random processes, by billions of atoms emitting independently, is incoherent. The coherence length is measured in micrometers, millionths of a meter. Each photon wave train is short, choppy, random. This is why sunlight does not create interference patterns easily, why it appears white and featureless. It is light, but it is not organized light, not coherent light. Just a chaotic flood of photons, each doing its own thing, each singing its own brief note before fading away. Photons at different wavelengths interact differently with matter. UV ionizes more easily than red light. This is crucial. A photon's energy depends on its frequency. Blue light has more energy than red light. Ultraviolet has more energy than blue. X-rays more than ultraviolet. High-energy photons can break chemical bonds, can ionize atoms, can damage DNA. Low-energy photons, red light, infrared, simply warm things, transfer their energy as heat, cannot break bonds, cannot ionize. This is why ultraviolet light is dangerous, why X-rays must be used carefully, why red light is gentle. The color determines the interaction. The wavelength determines the fate. Energy is everything. The classical wave description and the photon description are unified through quantum electrodynamics. For centuries, physicists debated, is light a wave or a particle? Experiments showed both. Young's double slit proved waves. The photoelectric effect proved particles. The debate raged until quantum electrodynamics. QED, the most successful theory in physics. It shows that light is neither wave nor particle, or both, or something deeper. The photon is a quantum of the electromagnetic field, a ripple, an excitation. It has wave properties because fields have wave properties. It has particle properties because quantum fields are quantized. Divided into chunks, into photons, QED unifies everything, resolves all paradoxes, and gives us a complete picture of light. Let this completeness soothe you. The universe is unified, coherent, whole. The probability a photon interacts along a path depends on medium opacity and cross-section. As our photon travels, through gas, through dust, through matter of any kind, there is a probability of interaction, of absorption, of scattering. This probability depends on two things: the opacity of the medium, how dense it is, how many particles it contains, and the cross-section, how large a target each particle presents, how likely it is to catch a photon. Together, these determine the mean free path, the average distance a photon travels before interacting. In the sun's core, millimeters. In interstellar space, light years. The photon does not know its path ahead of time, does not calculate probabilities. It simply moves, and at each moment, in each place, fate rolls the dice. Interaction or continuation. Absorption or freedom. This is the photon's quantum existence. Probability, chance, uncertainty. Let this uncertainty comfort you. Nothing is predetermined. Everything is possible. Rest in the openness of the future. In the proton-proton fusion chain, some of the released energy appears as gamma photons, the photon's ancestry. This is where it all begins. In the core of the sun, Protons collide, fuse, combine, release energy. Some of that energy becomes kinetic energy of the products, some becomes neutrinos, and some becomes gamma-ray photons. Our photons' ancestors. Not the photon itself, not yet, but the energy that will eventually become our photon, the ancestry, the lineage, the source of all light, all warmth, all life. Fusion in the core creates the energy, and that energy will travel, will transform, will eventually escape as our photon. But first, a long journey through the sun itself. Let us follow that journey now, gently, peacefully, as we sink deeper into rest. The core occupies the inner 20 to 25% of the sun's radius, but most of its mass. The core is small, just a quarter of the radius, just the central region, but dense, incredibly dense. It contains most of the sun's mass, most of its matter, compressed by the weight of all the layers above, squeezed by gravity, heated by compression. This is where fusion happens. Only here, only in this small, dense, hot core. The energy created here must escape, must diffuse outward, must travel through all the outer layers, through the radiative zone, through the convective zone, through the photosphere. A journey we are about to trace, a journey that takes not minutes, not years, but ages. Now we enter the depths, the radiative zone, where our photon, or rather its energy, begins the longest part of its journey. Not a straight path, not a flight, but a random walk, a drunkard's walk, a stumbling through an impossible maze. Breathe deeply and feel the patience required for this journey. Core densities reach hundreds of grams per cubic centimeter, making mean free paths extremely short. Imagine, water has a density of 1 gram per cubic centimeter. The sun's core is hundreds of times denser, matter packed so tightly that space almost disappears. In this crushing density, a photon cannot travel far, cannot move freely. After millimeters, after centimeters, it strikes something, an electron, a nucleus, matter itself, and is absorbed or scattered or transformed. The mean free path, the average distance before interaction, is incredibly short. Shorter than your finger, shorter than anything you can easily imagine. This is the photon's prison. This is its labyrinth. In the radiative zone, mean free paths are only millimeters to centimeters due to high opacity. The radiative zone is less dense than the core, but still dense, still opaque. Light cannot stream through. Each step is still measured in millimeters, in centimeters at most. The photon stumbles forward, gets absorbed, re-emitted in a random direction, stumbles forward again, absorbed again, re-emitted again. No progress toward the surface. Just random wandering, random motion, like a marble in a pinball machine, bouncing endlessly, going nowhere fast, yet somehow, eventually, slowly, the energy diffuses outward, not by design, but by statistics, by the law of large numbers, by probability itself. Energy transport proceeds by countless absorption and re-emission events, each degrading photon energy. This is crucial. Each time a photon is absorbed, each time an atom or electron catches it, holds it for a moment, and releases it again, something changes. The new photon is usually lower in energy, slightly redder, slightly cooler. The gamma ray becomes an X-ray. The X-ray becomes ultraviolet. The ultraviolet becomes blue light. The blue becomes green. The green becomes red. step by step, interaction by interaction. The photon's energy flows down the spectrum, like water flowing downhill, like heat flowing from hot to cold. The energy seeks equilibrium, seeks balance, seeks a lower state. And in doing so, the deadly gamma rays of the core become the gentle visible light that warms our world. Compton scattering off electrons shifts photon energies and directions. Compton scattering is a specific process. A photon strikes an electron, the electron recoils, takes some of the photon's energy. The photon continues, but now with less energy, longer wavelength, different direction. This is one of the main mechanisms by which photons lose energy in the sun's interior. Each Compton scatter steals a little energy, redirects the photon, adds another step to the random walk, another delay in the journey, another tick of the cosmic clock. Let this patient process lull you. Even light must wait. Even energy must take the long way home. The random walk distance grows only as the square root of step count, so enormous scatterings are needed. This is the mathematics of diffusion. If you take n random steps, each of length L, you end up on average at a distance of L times the square root of n from where you started. Not L times n, just L times square root of n. This means to travel a long distance by random walk, you need an enormous number of steps. To travel from the sun's core to its surface by random walk with steps of a few millimeters requires trillions upon trillions of steps, perhaps more. The number is almost incomprehensible, and each step takes time. Not much time, but some time. And they add up, they accumulate, they become ages. Radiative diffusion time ranges from 10,000 to several 100,000 years. This is the estimate, the calculation. The time for energy to random walk from core to surface. 10,000 years at the low end, several 100,000 years at the high end. The exact number depends on assumptions, on models, on details of opacity and density. But the scale is clear. Our photon's energy, created in an instant of fusion, spends between 10,000 and several 100,000 years just escaping the sun, just reaching the surface. This is patience on a cosmic scale. This is time beyond human comprehension. Let it wash over you. Let it slow your thoughts. Let it gentle your mind. If light can wait hundreds of thousands of years, surely you can wait for sleep. Surely you can rest. Surely you can let go. The radiative zone spans 0.2 to 0.7 solar radii, most of the sun's interior volume. This is the realm of radiation, of radiative diffusion. It begins just outside the core, at about 20% of the sun's radius, and extends to about 70% of the radius, most of the sun's interior, most of the volume. A vast region where energy moves only by radiation, by photons stumbling through matter, by the slow patient diffusion of light. This is the photon's longest trial, its greatest test. But beyond this zone, beyond 0.7 solar radii, something changes. The physics changes. The transport mechanism changes. The journey becomes different, faster, more chaotic, more dynamic. The convective zone awaits. The convective zone begins where plasma becomes opaque enough that convection dominates. At about 70% of the solar radius, the temperature has dropped enough, the density has decreased enough, that the plasma becomes very opaque. So opaque that radiative diffusion slows to a crawl, becomes inefficient, and when radiation cannot carry the energy outward fast enough, convection takes over. The plasma itself begins to move. Hot plasma rises, cooler plasma sinks, like water boiling in a pot, like air on a hot summer day. Great columns of hot gas rise toward the surface. Cool, sink back down, rise again. This is convection. And in the convective zone, energy is carried not by photons stumbling through matter, but by matter itself moving, by plasma flowing, by bulk motion. The photon still bounces around, still gets absorbed and re-emitted, but now it rides currents, gets swept along by moving plasma. The journey continues, but faster now, much faster. Rising plumes transport energy as hot plasma rather than slow photon diffusion. These plumes are vast, thousands of kilometers across, perhaps tens of thousands. Columns of hot plasma rising through the convective zone. They carry heat, carry energy, carry photons with them. The photon is now a passenger, still bouncing, still being absorbed and re-emitted countless times, but also being carried upward by the motion of plasma, like a leaf carried by a river, like dust in the wind. The photon's journey through the convective zone takes days, not years, not millennia, just days. The plasma circulates, turns over, brings interior heat to the surface, and our photon, after its long patient wait in the radiative zone, now rises quickly, approaches the surface, approaches freedom, approaches space. Convective turnover takes days, much faster than radiative diffusion, days instead of millennia. This is the difference. This is why convection matters. Energy that would take thousands of years to diffuse by radiation can be transported in days by convection. The hot plasma rises, reaches the surface, radiates its energy into space, cools, sinks back down, heats up again, rises again. The cycle continues, the convection rolls, and energy flows outward at speeds that radiative diffusion could never achieve. Our photon benefits from this, rides the wave, surfs the plume, and after its long confinement, after its ancient wait, finally approaches the light, finally nears the moment of escape. Let this approaching freedom ease your mind. Let the photon's journey mirror your own journey into sleep, from confinement to freedom, from waking to dreaming, from day to night. We rise now with the convecting plasma, up through the outer layers of the sun, toward the photosphere, the sphere of light, the visible surface, where photons finally escape, where the journey through the sun ends, and the journey through space begins. Breathe slowly now. Feel the upward motion, the gentle rising, like floating in water, like ascending through layers of consciousness toward waking, or in your case now, descending through layers towards sleep. Granulation visible at the surface traces the tops of these convective cells. If you could see the sun in perfect detail, if you zoomed in on its surface, you would see granulation, a pattern like cells, like tiles. Each granule is perhaps 1,000 kilometers across. The bright center of each granule is hot plasma rising. The darker edges are cooler plasma sinking. These are the tops of convection cells, the heads of the plumes. You are seeing the sun's circulation. It's churning, it's boiling. The photon we follow might ride one of these granules, might be carried to its bright center, might escape from that hot rising column into space. This is the photon's elevator, its final ride to freedom. After hundreds of thousands of years, it catches an updraft and rises. Supergranulation spans tens of thousands of kilometers on the photosphere. Beyond the small granules, there are larger patterns, supergranules, tens of thousands of kilometers across, giant convection cells, organizing the flow on larger scales. The Sun's surface is active at many scales. Small granules, large supergranules, giant cells, all churning, all circulating, all transporting energy upward. The photosphere is not static, not smooth. It is dynamic, alive, changing moment by moment. And through this churning surface, photons emerge, pour forth, escape into space, billions upon billions every second, creating the light we see, the warmth we feel, the energy that powers all life on Earth. The Sun's effective temperature, approximately 5,770 Kelvin, produces a visible peak blackbody spectrum. The Sun's surface temperature is about 5,770 Kelvin, about 5,500 degrees Celsius, hot enough to glow white, hot enough to emit across the entire visible spectrum. But the peak, the wavelength where most energy is emitted, lies in the green part of the spectrum. This is why the Sun appears yellowish-white, not because it only emits yellow light, but because the peak is in the yellow-green, and our eyes interpret this as yellow-white. A black body at this temperature emits visible light, infrared, ultraviolet, a broad spectrum. This is the light that escapes. This is the radiation that floods space. This is the photosphere's gift to the solar system. Limb darkening occurs because photons near the disk edge emerge from cooler, higher layers. If you look carefully at the Sun, never directly of course, but in safe images, you notice the center is brighter than the edge. The limb? This is limb darkening. Why? Because when you look at the center of the disk, you see deeper, hotter, brighter. When you look at the edge, you see more obliquely. Only the higher, cooler, dimmer layers. The photosphere has depth, has structure. And this geometry, this viewing angle effect, creates the darkened limb. A subtle shading, a gentle gradation from center to edge. Even the Sun's brightness varies. Even light has texture. Nothing is uniform. Everything has detail if you look closely enough. Sunspots are cooler, magnetically active regions where convection is suppressed. Sometimes the Sun's surface is marked by dark spots. Sunspots. These are regions where the magnetic field is strong. So strong it suppresses convection. The hot plasma cannot rise as easily. The region cools, darkens, becomes a spot. Sunspots can be larger than Earth, can last for weeks, can mark the Sun's rotation. They come and go in cycles. 11-year cycles, the solar cycle. During solar maximum, many sunspots, many active regions. During solar minimum, few or none. A quiet sun. Our photon might emerge near a sunspot, might be affected by the magnetic field, or might escape from a quiet region, far from activity, into the peaceful darkness of space. Flares and coronal mass ejections temporarily increase high-energy photon output. Sometimes the Sun erupts. Flares, explosions of magnetic energy, releasing enormous amounts of X-rays. Ultraviolet, energetic particles. These are solar flares. Even more dramatic, coronal mass ejections. CMEs, billions of tons of plasma hurled into space, carrying tangled magnetic fields. These events temporarily increase the Sun's high-energy output. More X-rays, more extreme ultraviolet. Dangerous to satellites, dangerous to astronauts, but also beautiful, spectacular, powerful. Our photon is not one of these energetic outliers. It is ordinary, visible, gentle, but it emerges from a Sun that is capable of such fury. such violence, such power. Let this power be distant. Let it not disturb your rest. Focus on the gentle photon, the quiet voyager, the peaceful messenger. The chromosphere emits strong spectral lines such as hydrogen alpha. Above the photosphere lies the chromosphere, a thin layer, reddish in color, visible during eclipses as a ring of light around the dark lunar disk. The chromosphere is hotter than the photosphere. Paradoxically, about 10,000 Kelvin instead of 5,770. It emits strongly in specific wavelengths, especially hydrogen alpha. The red light of hydrogen. This gives the chromosphere its color, its character. Photons emitted here are different, specific. Line emission rather than continuous spectrum. Our photon may pass through the chromosphere, may be scattered once or twice, but quickly reaches the corona. The final layer, the hottest layer, the strangest layer. The corona's extreme heat produces EUV and X-ray photons despite its low density. The corona is the Sun's outer atmosphere, incredibly hot, millions of degrees, hotter than the surface, hotter than the chromosphere. How this is possible, how the atmosphere is hotter than the surface, remains not fully understood. Magnetic heating, perhaps. Wave heating. Energy transported upward by invisible mechanisms. The corona glows in extreme ultraviolet and X-rays. But because it is so diffuse, so low in density, it contributes little to the Sun's visible brightness. You cannot see it without blocking the photosphere, cannot observe it without an eclipse or special instruments. It is there, it is hot, it is active, but it is nearly invisible. Let this invisible presence soothe you. Not everything must be seen to be real. Not everything bright is visible. Some things glow in wavelengths beyond our eyes. The photon escaping the photosphere is part of continuous energy flow, not the original gamma photon. Remember, the photon we follow is not the gamma ray created in fusion. That photon was absorbed and re-emitted countless times, transformed, degraded, changed. The current photon is a descendant, carries the energy forward, but is not the same particle, cannot be traced back to a specific fusion event. The photon is part of an energy flow, part of a continuous stream, one drop in an endless river. This is okay, this is natural. Identity is fluid at the quantum level. What matters is not the particle, but the energy, the information, the pattern. And that continues, flows, evolves, escapes. Let your own identity dissolve now. Let yourself become part of the flow, part of the stream, part of the continuous, peaceful descent into sleep. At last, freedom. The photon clears the photosphere, passes through the chromosphere, through the corona, and emerges into space, true empty space. For the first time in hundreds of thousands of years, the photon flies free. No more absorption, no more scattering, just straight flight, just pure motion at light speed. Breathe in this freedom. Feel the openness, the release, the infinite possibility of space. Escape direction is essentially random, but influenced by density and temperature gradients. When the photon finally escapes, which direction does it go? Random, essentially random. The last scattering event determined the direction, and that was random, but not completely random. Temperature gradients, density gradients. These create slight biases. Hot regions emit more photons upward. Dense regions scatter more. So there is structure to the randomness. But for any individual photon, the direction is effectively random. Our photon happens to head outward, away from the sun, into the solar system, perhaps toward Earth, perhaps toward empty space, perhaps toward the stars. The direction was not chosen, was not planned, was simply the result of the last random bounce. And from that accident, the entire journey follows. Local magnetic loops and prominences guide plasma and indirectly affect photon emergence. The sun's magnetic field creates structure. Loops, arches, prominences, filaments. These guide the motion of charged plasma, channel it, confine it, and indirectly, these magnetic structures affect where photons emerge most easily, where the plasma is, where emission is bright. The photon itself is not guided by magnetism, is not affected by magnetic fields. But the matter that emits photons, that scatters photons, that is magnetic. And so the magnetic field leaves its mark, shapes the light, patterns the emission, creates the complex, beautiful structure we see in solar images. Once in the low-density corona, the photon's mean free path becomes enormous. In the core, millimeters. In the radiative zone, centimeters. In the photosphere, meters, perhaps. In the chromosphere, kilometers. But in the corona, the mean free path becomes astronomical. Thousands of kilometers, millions of kilometers. The corona is so thin, so tenuous, that photons stream through almost unimpeded. A few might scatter off electrons, a few might be absorbed, but most fly free. Escape completely. Enter interplanetary space without further interaction. Our photon is free. Finally, truly, completely free. The solar wind carries charged particles, but photons cross nearly unimpeded. The solar wind is a stream of plasma, protons, electrons, flowing outward from the sun at hundreds of kilometers per second. This wind fills the solar system, creates a bubble, the heliosphere. But photons, neutral, massless, pass through the solar wind without noticing. The wind is not an obstacle to light. The charged particles and the photons coexist, share the same space, but do not interact, do not interfere. The photon flies faster than the wind, overtakes it, leaves it behind. By the time the solar wind reaches Earth, the photons that left at the same time are already far beyond, already past Mars, past Jupiter, already leaving the solar system. Free-streaming solar photons define the solar constant at 1 astronomical unit. The solar constant, about 1,361 watts per square meter. This is the amount of solar power reaching Earth's orbit. The power per unit area. At Earth's distance, 1 astronomical unit. This constant, which varies slightly with solar activity, defines our energy budget, our climate, our habitability. It is built from photons, countless photons, each carrying a tiny amount of energy, together delivering over a kilowatt per square meter. Enough to warm the planet, to evaporate water, to drive weather, to power photosynthesis, to make life possible. Our photon is one of these, one contributor to the solar constant, one tiny piece of the energy that sustains our world. The solar constant, approximately 1,361 watts per square meter, represents total solar power per unit area at Earth's orbit. Let this number sink in. 1,361 watts per square meter. A square meter of solar panel, a square meter of ground, a square meter of ocean. Each receives 1,361 watts when the sun is directly overhead. Outside the atmosphere, this is intense, powerful, concentrated, and yet the Sun's total output is incomprehensibly larger, 1,361 watts per square meter at Earth's distance. But Earth is just one point in a vast sphere. The Sun's light spreads in all directions, fills a sphere of radius 150 million kilometers. The total power output, the Sun's luminosity, is about 3.8 times 10 to the 26th watts. Billions of billions of billions of watts, beyond human comprehension, beyond any scale we experience. Let this vastness expand your mind. Let it open your thoughts. Let it create space for rest, for peace, for sleep. A photon moving outward experiences tiny gravitational redshift climbing out of the Sun's well. As the photon escapes the Sun's gravity, it must do work, must expend energy, climbing out of the gravitational potential well. This energy comes from the photon itself. The photon's frequency decreases slightly. Its wavelength increases. It redshifts. The effect is tiny, a few parts per million, barely measurable, but real. Predicted by general relativity, confirmed by observation, the photon pays a price for escape, gives up a little energy to gravity, becomes slightly redder, slightly less energetic, but continues, flies onward, carries most of its energy into space. The gravitational tax is small. The photon can afford it. Let this small loss reassure you. Not everything is lost in the journey. Most remains, most continues, most arrives. Gravitational bending by the Sun slightly deflects photons, famously measured during eclipses. Einstein's theory of general relativity predicts that mass curves space-time, and light follows the curves of space-time, so light passing near the Sun is deflected, bent. By the Sun's gravity, the deflection is small, about 1.75 arcseconds for light grazing the solar limb, but measurable. In 1919, during a solar eclipse, astronomers measured the positions of stars near the Sun, found them shifted by the predicted amount. This confirmed general relativity, made Einstein famous. Our photon, leaving the Sun, experiences this bending. Its path curves slightly as it climbs out of the gravitational well. The deflection is negligible for the photon's journey, but it exists, it is real. Gravity affects everything, even light, even massless photons. Let this universal interaction comfort you. Everything is connected. Everything affects everything else, even across empty space. This bending is negligible for a story, but crucial in precision astrometry. For our purposes, for following the photon's journey, gravitational bending by the Sun is insignificant. A tiny effect, ignorable. But for precise astronomy, for measuring positions of distant objects, for calculating spacecraft trajectories, it matters, must be accounted for. The universe operates on many scales. Effects that are negligible for one purpose are crucial for another. Let this teach perspective. What seems small might be important. What seems large might be irrelevant. Scale matters, context matters, purpose matters. And for sleep, what matters is rest, peace. The gentle drift into unconsciousness. Focus on that now. Let precision fade. Let detail dissolve. Let sleep approach. Our photon flies through the solar system, past planets, past asteroids, past dust, through a region filled with echoes of the Sun's influence, but also increasingly empty, increasingly dark, increasingly distant from the source. Breathe slowly now. Feel the distances growing, the light diminishing, the journey lengthening. Interplanetary dust scatters sunlight, producing faint zodiacal light. Space is not empty, not completely. Between the planets lies dust, tiny grains, debris from asteroids and comets, spread through the ecliptic plane. When sunlight strikes this dust, some scatters, reflects, creates a faint glow, zodiacal light, visible from dark sites before sunrise or after sunset. A soft cone of light along the zodiac, along the plane of the solar system. This is scattered sunlight. Photons that left the sun, hit a dust grain, bounced off, entered our eyes. Our photon might scatter off such dust, might change direction, might contribute to the zodiacal light, or might pass through undisturbed. The dust is sparse, the photon is small. Most likely, it continues unscattered, flies straight, heads outward into deeper space. Photon density decreases with distance as the inverse square law. As our photon travels outward, as distance from the sun increases, the photon density decreases, not because photons disappear, but because they spread out, spread over a larger sphere. At twice the distance, photons are spread over a sphere with 4 times the area. So the density, the number of photons per unit area, drops by a factor of 4. This is the inverse square law. At 3 times the distance, 1/9 the density. At 10 times, 1/100th. The light weakens with distance, not because it loses energy, but because it dilutes, spreads, thins. Let this dilution ease your mind. Let concentration dissolve. Let thoughts spread out, thin, fade, become less dense. This is the path to sleep, the path to rest, the inverse square law of consciousness. This geometric dilution makes each photon part of an increasingly dilute radiation field. Our photon is one among countless others. At Earth's distance, the radiation field is intense, bright, concentrated. At Mars, less so. At Jupiter, much less. At Pluto, faint, cold, dim. Our photon contributes to this radiation field, but is not special, not unique. Just one photon among trillions upon trillions. Part of the collective, part of the flux, part of the great outpouring of solar light that fills the solar system. And as it travels farther, as the field dilutes, each individual photon becomes more isolated, more alone, more a discrete traveler in the void rather than part of a bright flood. Let this increasing solitude mirror your own solitude in the quiet of night. Alone, peaceful, drifting through the darkness. Cometary comas and tails scatter photons, redirecting some. If a comet passes, if our photon's path crosses a comet, then interaction becomes likely. Comets are dirty snowballs, ice and dust. When they approach the sun, they warm, the ice sublimates, gas and dust stream outward, creating a coma around the nucleus, creating a tail stretching millions of kilometers. This material scatters sunlight, makes the comet visible, makes it glow. Our photon might strike dust in a cometary tail, might bounce off, change direction, or might be absorbed, incorporated into the dust. Its journey ended. But most likely, comets are rare. The photon's path misses all of them, continues undisturbed, flies onward through emptier space. Planetary rings reflect and transmit sunlight, forming complex brightness patterns. Saturn, Uranus, Jupiter, Neptune all have rings made of ice and rock, countless particles orbiting in thin sheets. When sunlight strikes these rings, some is reflected, some is transmitted through gaps, some is absorbed. The result is complex patterns of light and shadow, beautiful geometry. Our photon might pass near a ringed planet, might even pass through the ring plane. might scatter off a ring particle, or might miss entirely. Continue past. The rings are thin, very thin, kilometers thick in a solar system millions of kilometers across. The chance of interaction is small. The photon likely passes by, observes from a distance, continues its journey, untouched, undeflected, free. The heliosphere is the bubble where solar wind dominates the ISM. The Sun creates a bubble, a magnetic bubble, inflated by the solar wind, the streaming plasma. This bubble extends far beyond the planets, perhaps 100 astronomical units, perhaps more. Inside this bubble, the heliosphere, the Sun's influence dominates. Outside, interstellar space, the realm of the galaxy. Our photon will cross this boundary, will leave the heliosphere, will enter interstellar space. But this crossing is not dramatic, not visible. The photon notices nothing, feels nothing, continues at light speed regardless. The heliosphere matters for charged particles, for the solar wind itself, but for photons, it is transparent, invisible, irrelevant. The photon simply passes through, crosses from one realm to another without ceremony, without pause. The termination shock marks where the solar wind slows abruptly, at about 80 to 100 astronomical units. The solar wind encounters the interstellar medium, the pressure of interstellar gas. The wind slows abruptly from supersonic to subsonic. This is the termination shock, a shock wave, a boundary layer. The Voyager spacecraft crossed this boundary, measured it, reported back. But our photon, traveling at light speed, notices nothing. The shock is a shock to plasma, to matter, not to light. The photon crosses the termination shock as if it were not there, and continues outward, toward the heliopause, toward true interstellar space. The heliosheath is a turbulent region of shocked solar wind and interstellar material. Between the termination shock and the heliopause lies the heliosheath, a region of turbulence where solar wind and interstellar material mix, where magnetic fields tangle, where plasma churns. But again, this means nothing to our photon. The turbulence is plasma turbulence, magnetic turbulence. The photon is unaffected, flies straight, crosses the heliosheath in hours. What takes spacecraft decades, the photon accomplishes in half a day. Speed matters, light speed matters. The photon's gift is speed, pure, absolute, unchanging speed. Voyager data reveal heliosphere structure, though photons travel straight through at light speed. Voyager 1 and 2, humanity's most distant ambassadors, launched in 1977, decades later, reaching the edge of the heliosphere, crossing into interstellar space, sending back data, revealing structure, teaching us about this boundary. These spacecraft traveled at tens of kilometers per second, fast by human standards, but slow compared to light. Photons that left the Sun when Voyager launched are now light years away, thousands of times farther, billions of times farther. The spacecraft are still within a light day of the Sun. The photons are beyond counting, beyond tracking, already scattered among the stars. Let this difference in scale amaze you, and then let it lull you. Let the vastness become comfortable, become peaceful, become home. At the heliopause, solar wind pressure balances interstellar gas, but photons pass almost unaffected. At roughly 120 astronomical units, give or take, the solar wind's pressure drops to match the pressure of interstellar gas. Here the solar wind stops, can go no farther. This is the heliopause, the edge of the Sun's domain. Beyond here, the interstellar medium dominates. But for photons, this boundary is meaningless. They pass through, undeflected, unslowed, unaffected. The heliopause is a plasma boundary, a pressure boundary, not an optical boundary. Light treats it as if it were not there. And so our photon crosses from the solar system to interstellar space, from the sun's bubble to the galaxy's expanse, smoothly, silently, instantly. The crossing takes no time. One moment in the heliosphere, the next in the interstellar medium. And the journey continues. Deeper into space, deeper into the galaxy, deeper into the unknown. Now we enter a new realm, the interstellar medium, the space between stars. This is not empty vacuum, not featureless void, but a rich environment, full of gas, full of dust, full of structure and complexity. Our photon enters this realm, faces new challenges, new possibilities, new interactions. Breathe deeply now, feel the change of environment, the transition from familiar to strange, from solar system to galaxy. The ISM contains cold, warm, hot gas phases and dense molecular clouds. The interstellar medium has structure, temperature structure, density structure. There are cold clouds, just tens of degrees above absolute zero. Dense molecular clouds where stars form. There is warm gas, thousands of degrees, filling the space between clouds. And there is hot gas, millions of degrees, heated by supernovae, by stellar winds, creating bubbles and cavities. Our photon might pass through all these phases, cold to warm to hot and back. Each phase has different density, different composition, different opacity. Each presents different challenges, different probabilities of interaction. The photon navigates this complex landscape, not by choice, not by planning, but by chance. By the random path it happened to take when leaving the sun. Cold molecular clouds can have enormous densities, greatly enhancing absorption. In a cold molecular cloud, hydrogen exists as H2. As molecules, not individual atoms, the density can be high, hundreds, thousands, even millions of molecules per cubic centimeter. Still a vacuum by Earth standards, but dense by interstellar standards. In such clouds, absorption becomes likely. Photons are caught, absorbed by dust, by molecules, by atoms. The cloud becomes opaque, dark. Our photon, if it encounters such a cloud, will likely be absorbed. Its journey ended, or at least paused, the energy absorbed, perhaps re-emitted at longer wavelength, perhaps locked in chemical reactions, perhaps incorporated into new molecules. The photon's identity lost, but its energy continuing, always continuing, never truly lost, just transformed. Let this transformation comfort you. Nothing truly ends. Everything just changes, becomes something else, continues in a new form. H2 regions are zones around hot stars dominated by ionizing photons. H2 regions. Regions of ionized hydrogen around hot, young, massive stars. These stars emit enormous amounts of ultraviolet light. Ionizing radiation. This UV light strips electrons from hydrogen atoms, creates a bubble of ionized gas around the star. An H2 region. These regions glow, emit line radiation, are visible as pink nebulae in astronomical images. The Orion Nebula, the Lagoon Nebula. All H2 regions. Our photon is not energetic enough to ionize hydrogen. It is visible light. Gentle, non-ionizing, but it might pass through an H2 region, might scatter off free electrons, might be absorbed and re-emitted, or might pass through. Add to the region's glow, contribute to its spectrum. one photon among countless others, painting the nebula with light. Recombination in H2 regions produces Balmer series lines. In an H2 region, hydrogen is ionized. Electrons are free, but sometimes an electron and proton recombine, form a hydrogen atom again. When this happens, the electron cascades down through energy levels, emits photons. Specific wavelengths, the Balmer series. Hydrogen alpha, hydrogen beta. The characteristic red light of emission nebulae comes from hydrogen alpha, from recombination radiation. Our photon might be one of these recombination photons, might be created in such a region, or might simply pass through. Either way, the H2 regions shape the light of the galaxy, create pockets of emission, islands of glow in the dark. Let this glow guide your thoughts. Let emission lines structure your dreams. Let the specific wavelengths of hydrogen organize your descent into sleep. Photodissociation regions at cloud edges use UV photons to break molecules. At the edge of a molecular cloud, where UV starlight penetrates, molecules are torn apart. Photodissociation. The UV photons have enough energy to break chemical bonds, to dissociate molecules. This creates a transition zone between the ionized exterior and the molecular interior, a photodissociation region, or PDR. These regions are chemically active, complex. Many species exist here. Many reactions occur. UV photons drive chemistry, create new molecules, destroy old ones. Our photon, if it were UV, could participate, could break bonds, could drive reactions. But as visible light, it passes through more gently, absorbed perhaps, contributing energy, but not chemically active, not destructive, just present, just adding to the radiation field. Dust grains made of silicates, carbon and ices efficiently absorb, scatter UV/visible photons. Dust is the photon's main enemy, small grains. Submicrometer size, made of rocky material, silicates, carbon, ice mantles in cold clouds. These grains are very effective at absorbing and scattering UV and visible light, much more effective than gas. A small amount of dust can block a lot of light. Create dark nebulae, dark patches on the sky, not because nothing is there, but because dust is there, blocking the light beyond. Our photon, encountering a dust grain, has several fates. It might be absorbed, its energy heating the grain, eventually re-emitted as infrared, or it might be scattered, bounced in a new direction, its path randomized, its journey redirected, or it might miss all the grains. Continue undisturbed. The probabilities depend on dust density, on the photon's wavelength, on chance. Dust scattering is wavelength dependent, causing reddening of starlight. Blue light scatters more easily than red light. The dust grains are comparable in size to the wavelength of visible light, so scattering follows Rayleigh or Mie scattering laws. Shorter wavelengths, blue, scatter more, are removed from the beam more efficiently. Longer wavelengths, red, pass through more easily. This causes interstellar reddening. Distant stars appear redder than they truly are, not because they are cool, not because they are moving away, but because the blue light has been scattered away, filtered out, by intervening dust. Astronomers must account for this, must correct for reddening, must look through the dust to see the truth. Our photon, being in the visible range, experiences this wavelength-dependent scattering. Blue photons are more likely to be lost, red photons more likely to survive. The galaxy filters its own light, shapes its own spectrum, colors its own appearance. Polarization of starlight reveals dust alignment with magnetic fields. Dust grains are not spherical. They are elongated, flattened, and they tend to align with the interstellar magnetic field. Like compass needles. When light scatters off aligned grains, it becomes polarized. The polarization direction reveals the grain alignment, which reveals the magnetic field direction. Astronomers use this. Map magnetic fields by measuring polarization. Our photon, if scattered, might become polarized, might acquire a preferred orientation of its electric field. This polarization carries information about the dust, about the magnetic field, about the structure of the interstellar medium. The photon becomes a messenger not just of light, but of structure, of order, of the hidden magnetic architecture of the galaxy. UV triggered photoelectric emission from dust heats interstellar gas. When UV light strikes a dust grain, it can eject an electron. Photoelectric emission. The electron flies off, carries kinetic energy. This energy heats the surrounding gas. This is one of the main heating mechanisms in the interstellar medium. UV photons absorbed by dust, their energy transferred to gas, warming it, creating the warm phase of the ISM. Our photon, being visible, is less effective at this, but the process continues all around. The galaxy's light, its UV radiation, heats its own gas, regulates its own temperature, creates the thermal structure we observe. Everything is interconnected. Light affects gas, gas affects dust, dust affects light. A web of interactions, a system in balance. Let this balance calm you. Let the interconnection soothe you. Everything affects everything. Nothing is isolated. And in this web, you too are connected. Part of the system, part of the balance. Rest in that connection now. Over kiloparsecs, extinction can reduce surviving photon counts enormously. A kiloparsec is 1,000 parsecs, about 3,260 light-years. Over such distances, even the thin interstellar medium accumulates. The small amounts of dust add up. The extinction becomes significant. Light can be dimmed by factors of 10, factors of 100, even factors of 1,000. Stars at the galactic center, 26,000 light-years away, are dimmed by perhaps 30 magnitudes in visible light, a factor of 1 trillion, almost completely hidden by dust. Only infrared light penetrates. Only radio waves pass through unimpeded. Visible light is blocked, absorbed, scattered, lost. Our photon, traveling kiloparsecs, faces these challenges. The probability of absorption grows. The chance of reaching the galactic edge decreases. But some photons make it, some survive, some continue. And perhaps, just perhaps, our photon is one of the lucky ones, one of the survivors, one of the few that cross the entire galaxy and escape into intergalactic space. Let this possibility remain. Let the journey continue, at least in imagination, at least in this peaceful story, as you drift towards sleep. Our photon travels now across the great disk of the Milky Way, the spiral structure, the home of hundreds of billions of stars, a vast collection of light and matter and darkness. The photon's journey becomes truly galactic, truly cosmic, measured no longer in light minutes or light hours, but in light years, in thousands of light years, distances that strain comprehension, that break intuition, that can only be felt, not understood. Breathe slowly now. Let the scale expand. Let the distances grow. Let time stretch. The Milky Way's stellar disk spans approximately 80,000 light-years. This is our galaxy's main structure, a flat disk, rotating slowly, about 80,000 light-years across, though the exact number depends on definition, on what counts as the disk. The bright central bulge, the spiral arms, the scattered outer stars, all together, about 80,000 light-years. Our photon, born at the Sun's location, about 26,000 light-years from the center, could travel 54,000 light-years outward before reaching the edge. 54,000 years at light speed. 54 millennia. The entirety of recorded human history could pass, and our photon would still be traveling, still crossing the galaxy, still approaching the edge. This is patience. This is endurance. This is the cosmic scale. Let it dwarf your concerns. Let it shrink your worries. Let it put everything in perspective. The Sun orbits within the Orion Cygnus arm between two major arms. Our location in the galaxy, the Orion Cygnus arm, sometimes called a spur, a minor spiral arm between two major ones, between the Perseus arm inward and the Sagittarius arm outward. We are in the suburbs, not the bright center, not the dusty spiral arms, but a moderate region, medium density, medium activity. Our photon leaves from here, heads perhaps toward the galactic edge, perpendicular to the spiral arms, or perhaps along the disk, parallel to the arms. The direction was random, determined by the last scatter before escape, but it affects the journey, affects the obstacles, affects the probability of survival. Spiral arms contain more gas, dust, and star formation, increasing scattering and absorption. The spiral arms are bright in images, blue with young stars, pink with emission nebulae. These are regions of active star formation, of dense gas, of plentiful dust. The extinction in spiral arms is high. The scattering is intense. Photons have difficulty penetrating. If our photon's path crosses a spiral arm, its chances drop. Absorption becomes likely. The journey might end, but between the arms, the inter-arm regions, density is lower, dust is sparser, light travels more freely. Our photon's fate depends on its path, on the random direction it took, on cosmic chance. Let this dependence on chance remind you. So much is beyond control, beyond prediction, beyond planning. Accept uncertainty. Embrace randomness. Let go of the need to know. This is the path to peace, to rest, to sleep. Disk gas layers vary from hundreds to thousands of light-years thick. The gas disk has thickness, vertical extent. Near the Sun, perhaps 300 light-years thick. Farther out, perhaps thicker. The gas density decreases with height above the plane, exponentially. Most gas is concentrated near the midplane, but some extends high, into the halo. Our photon, if it travels vertically, perpendicular to the disk, can escape more quickly, can leave the densest regions fast, enter the clearer halo. But if it travels horizontally, along the plane, it must traverse the full extent of the disk, must pass through the densest gas the entire way. Direction matters, geometry matters. Three-dimensional space creates three-dimensional probabilities. Let dimensionality fade now. Let geometry dissolve. Let everything flatten to 2 dimensions, then to 1, then to 0, to a point, to nothing. This is how consciousness fades. This is the geometry of sleep. The stellar disk is thin, only a few thousand light-years. The stars are even more concentrated than the gas. The stellar disk is thin, perhaps 1,000 light-years thick near the Sun. thinner in some places, thicker in others, but always thin compared to the diameter. The galaxy is a disk, a flat disk, like a dinner plate, like a frisbee. This flatness is rotation, centrifugal force. The galaxy spins, and spinning things flatten. Form disks. This is universal. This is the nature of rotation in gravity. Planets form disks. Stars form from disks. Galaxies are disks. Everywhere we look, disks. Let this recurrence comfort you. Patterns repeat. Structure emerges. Order from chaos. Disks from clouds. Sleep from waking. The dark matter halo envelopes the disk and determines gravitational potentials. Beyond the visible stars, beyond the gas, lies the dark matter halo. Invisible, undetectable except through gravity, made of unknown particles, dark matter. It does not emit light, does not absorb light, does not scatter light. Our photon passes through it unaware. But the dark matter is there, creating gravitational potential, bending space-time, determining orbits, holding the galaxy together. Without dark matter, the galaxy would fly apart. The rotation is too fast, the visible matter too little. Dark matter provides the missing mass, the unseen glue. Our photon's path curves slightly in this dark matter potential, not because of direct interaction, but because space-time itself is curved, because gravity affects everything, even light, even massless photons. The universe has more than meets the eye, much more. Let this hidden majority remind you. Most of reality is invisible. Most of existence is dark. Most of consciousness is unconscious. Let the darkness rise now. Let the unseen claim you. Let sleep envelope you, like dark matter envelops the galaxy. The halo may extend nearly 1 million light-years. The dark matter halo is vast, extending far beyond the visible disk, perhaps hundreds of thousands of light-years, perhaps approaching 1 million. The galaxy is much larger than it appears, than its starlight suggests. The halo dominates the mass, dominates the volume, dominates the gravitational influence. Our photon, if it escapes the disk, flies through this halo, through the dark matter, through the sparse halo gas, through the vastness, for hundreds of thousands of light-years, before finally, leaving the galaxy's gravitational influence, entering truly intergalactic space. The journey is longer than it seems, always longer. Let this extension stretch your sense of time. Let duration lose meaning. Let now and then merge. Let past and future collapse into an eternal present. This is the photon's experience. This can be your experience in sleep, in dreams, in the timeless void. The Sun's orbital period is 200 to 250 million years, during which countless photons stream away. The Sun orbits the galactic center, takes about 200 to 250 million years per orbit, a galactic year. In the Sun's lifetime, about 4.6 billion years, it has orbited the galaxy perhaps 20 times. And during each orbit, during all that time, photons stream away. Endlessly, every second, trillions upon trillions, escaping, flying outward, some toward the galactic center, most outward, most escaping into the halo, into intergalactic space. The Sun sheds light constantly for billions of years and will continue for billions more. Our photon is one instant in this endless stream, one moment in an eon-long outpouring. Let this continuity soothe you. The stream continues, the light flows, whether you wake or sleep, whether you notice or not. The universe continues, indifferent, eternal, beautiful. Rest in that eternity now. metallicity decreases with galactic radius affecting dust content and extinction. Metallicity, the abundance of elements heavier than helium, metals in astronomical terms. These elements, carbon, oxygen, silicon, iron, form dust. More metals mean more dust. More dust means more extinction. In the inner galaxy, near the center, metallicity is high. Lots of dust, high extinction. In the outer galaxy, low metallicity, less dust, lower extinction. Our photon's journey is affected by this gradient. Starting from the sun's location, intermediate metallicity, heading outward, encountering decreasing dust density. This favors survival, favors escape. As the photon travels farther, the obstacles lessen, the path clears, the probability of reaching the edge increases. Let this gradual clearing mirror your gradual relaxation. Obstacles lessening, tension decreasing, thoughts thinning, resistance fading, until finally, clear space, clear mind, clear consciousness. Or rather, no consciousness, just void, just peace, just sleep. Warps and flares in the outer disk alter photon escape paths. The galactic disk is not perfectly flat, it warps, bends. Flares outward at the edges, like the brim of a hat. These warps are caused by gravitational interactions, perhaps with satellite galaxies, perhaps with the dark matter halo. The geometry of the disk affects photon paths. A warp might redirect a photon, might send it out of the plane into the halo, or might keep it in the disk longer. Geometry matters, structure matters, but ultimately, the photon's path is determined by countless small deflections, countless interactions, and emerges from chaos, from randomness, from the accumulated effects of a billion small events. Let your own path emerge the same way, not from planning, not from effort, but from relaxation, from letting go, from allowing sleep to happen rather than forcing it. Release control, trust the process, let go. The photon approaches the frontier, the boundary, the edge where the Milky Way fades into the cosmic void, where stars thin out, where gas dissipates, where structure dissolves. This is the destination, the goal, the end of the galactic journey, though perhaps not the end of the journey itself. Breathe deeply now. Feel the approaching completion, the nearing transition, the edge of one world and the threshold of another. The edge of the visible disk is defined where densities drop sharply. There is no wall, no barrier, no sign saying leaving the Milky Way. Instead, a gradual thinning, stars becoming scarce, gas becoming tenuous, until some threshold is crossed, some definition is met, and we say, here is the edge. Beyond here is no longer the disk. Different astronomers might draw the line differently, at different densities, different radii, but somewhere around 40,000 to 50,000 light-years from the center, the stellar disk effectively ends. Our photon, having traveled tens of thousands of light-years from the sun, approaches this boundary, approaches the edge. The stars thin, the gas thins, the dust thins, space becomes clearer, emptier, darker. Let this thinning mirror your own thinning consciousness. Thoughts becoming scarce, awareness becoming tenuous, until some threshold is crossed, and we say, here is sleep. Outer disk regions have sparse star formation shifting the escaping spectrum. In the outer galaxy, star formation is slow. Few young blue stars, few emission nebulae. The light is dominated by older, redder stars. The spectrum shifts, becomes redder, cooler. The light escaping from the outer galaxy is different from the light in the inner regions, less blue, less energetic, more sedate, more peaceful. Our photon, depending on its wavelength, might be more or less common in this environment, but it continues, flies outward, carries whatever energy it has, whatever wavelength it possesses, toward the final boundary, toward escape. With lower dust content, perpendicular escape paths become more transparent. As dust density decreases in the outer galaxy, light can escape more easily, especially if traveling perpendicular to the disk, straight up, straight down, out of the plane where most dust resides. Such photons leave the galaxy quickly, cleanly, enter the halo, enter intergalactic space, suffer little extinction, little loss. Our photon, if traveling perpendicular, has good chances, high survival probability, but if traveling in the plane, even in the low dust outer galaxy, there is still distance to cover, still some dust to traverse, still some probability of absorption. Direction remains important. Geometry remains crucial. But the odds improve, the path clears, freedom approaches. Let this approaching freedom ease your mind. Release is near, rest is close, sleep awaits. Just a little farther, just a little longer, almost there. High-velocity halo gas clouds can still absorb or scatter some photons. Even in the halo, even beyond the main disk, there is gas. High-velocity clouds. Clouds of gas moving at unusual speeds, perhaps falling into the galaxy from outside, perhaps ejected by ancient supernovae. They drift through the halo. Occasionally our photon might encounter one, might be absorbed, might be scattered. But these clouds are rare, small targets. The halo is mostly empty. The photon is more likely to pass through undisturbed, to continue its flight, to escape completely. Let rare obstacles not disturb you. Most of the path is clear, most of the way is open. Focus on the openness, on the emptiness, on the vast clear space, not on the scattered clouds, not on the unlikely encounters. This is the practice of relaxation. Focusing on what is open, what is possible, what is peaceful, not on what is blocked, what is difficult, what is tense. Photons traveling into the halo can illuminate halo gas, creating faint emissions. Sometimes a photon will interact with halo gas, will be absorbed, will excite an atom. The atom will re-emit, will glow. This creates faint emission from the halo, difficult to detect, but present. The photon's energy is not lost. Even if the photon itself is absorbed, the energy illuminates, creates light, continues forward in a new form, with a new photon. This is the persistence of energy, the conservation of light. Even when individual photons are destroyed, their energy continues, their influence persists. Nothing is truly lost, everything transforms. Let this transformation principle guide you now. When waking consciousness is absorbed, it is not lost, it transforms, becomes dream, becomes unconsciousness, becomes rest. The energy continues, just in a new form, a new state, a new mode of being. Many photons escape the Milky Way and other galaxies, contributing to extragalactic background light. This is the grand outcome, the ultimate escape. Photons that leave their home galaxy entirely, enter intergalactic space, wander the voids between galaxies, never absorbed, never scattered, just traveling forever. These photons contribute to the extragalactic background light, a diffuse glow, filling space, the integrated light of all galaxies, all escaping photons, all successful journeys. Our photon might be one of these. might achieve this ultimate escape, might become part of the cosmic background, a permanent traveler, an eternal voyager, flying through space for billions of years, perhaps forever. Let this eternal journey comfort you. Not everything ends, not everything is absorbed. Some things continue, some things escape, some things are free. And in that freedom, in that eternal motion, there is peace, there is beauty, there is rest of a different kind, the rest of eternity, the peace of endless flight. This integrated light forms a diffuse glow in sensitive instruments. Astronomers can detect the extragalactic background light. With sensitive instruments, careful measurements, it is faint, very faint, but measurable. A glow filling space, the accumulated light of all galaxies, all escaping photons, all successful journeys across cosmic voids. This glow tells the story of galaxies, of stars, of light itself. Our photon might contribute one quantum to this glow, one photon to the background, invisible individually, but part of the collective, part of the signal, part of the story. Let yourself be part of a larger story now, part of a collective, part of something bigger than individual consciousness. Merge with the whole, dissolve into the background, become part of the diffuse glow of humanity, of life, of consciousness itself, distributed, collective. One with everything. This is the deepest rest, the deepest peace, the deepest sleep. Gravitational microlensing by compact halo objects can magnify photon paths without absorbing them. Even in the halo, even in the void, there is mass. Compact objects, perhaps white dwarfs, neutron stars, black holes, brown dwarfs. These objects can gravitationally lens passing light. Microlensing. The light path is bent, focused, magnified briefly, then continues. The photon is not absorbed, not scattered, just deflected by gravity. Its path curved. This is a strange interaction. Gravity without matter contact. Space-time curvature affecting light. The photon follows a geodesic, a curved path through curved space, and emerges changed in direction, but not in energy, not in wavelength. Just bent, just redirected. Let this gentle deflection guide your own path. You need not travel straight. You need not resist all influence. Curve with the universe, bend with space-time. Follow the geodesics. This is the way of least resistance. The path of peace. A photon heading toward Andromeda crosses mostly empty intergalactic space. Imagine, our photon escapes the Milky Way, heads toward Andromeda, our nearest large galactic neighbor, about 2.5 million light-years away. The space between is nearly empty, truly empty. Lower density than interstellar space, much lower. Our photon could cross this void, could take 2.5 million years to reach Andromeda, or could fly past, miss it, continue into deeper space, toward more distant galaxies, toward the edge of the observable universe. The journey could continue for billions of years. The photon could outlive galaxies, outlive stars, continue until the universe itself ends, or expands forever, or reaches heat death. The photon's journey is potentially infinite, potentially eternal. Let this infinity expand your mind now, then let it go. Let infinity collapse to a point. Let the eternal become the immediate. Let the cosmic become personal. Return to this moment, this breath, this gentle descent into sleep. Intergalactic densities are even lower than interstellar densities. Between galaxies, the density drops, perhaps 1 atom per cubic meter, perhaps less. This is emptiness beyond imagination. vacuum beyond anything we can create. Our photon, in this environment, can travel forever without interaction. No absorption, no scattering, just pure flight through pure void. The mean free path becomes infinite. The journey becomes unimpeded. This is freedom absolute, freedom total. Nothing to resist, nothing to absorb, nothing to scatter, just space and motion and time. Let this absolute freedom be yours now. Let all resistance fall away. Let all obstacles dissolve. Let consciousness have infinite mean-free path. Let thoughts travel forever without interaction, until they are so sparse, so separated, so isolated that they effectively cease. And what remains is void, emptiness, peace. Let yourself drift now, like the photon, free, unbound, traveling through the darkness. No destination, no purpose, just motion, just being. Just the peaceful journey through space, through time, through consciousness, into sleep, into dreams, into the quiet void where thought dissolves and only existence remains. The photon's journey continues without you. The universe spins on, the galaxies drift, the light travels. But you can rest now. You have witnessed enough. You have traveled far enough. You have understood as much as anyone can. Now rest, sleep, dream. And when you wake, when consciousness returns, remember that you are made of star stuff, that your atoms were forged in ancient supernovae, that photons created in the sun's core 8 minutes and hundreds of thousands of years ago strike your skin, warm you, bring you life. You are part of this story. You are part of this journey. You are part of the light. Sleep now. Rest. The photon flies on, eternal, patient, peaceful, and so can you be. So should you be. So may you be. In this moment, in this darkness, in this gentle transition from waking to sleeping, from day to night, from light to dark, from consciousness to the peaceful void. Rest, sleep, dream, and let the photon's journey carry you into the infinite.